Welcome back. This is unit 9.1. We're starting a new unit today, and this first section is on identification of acids and bases. You can find most of this information in chapter 17 of your book. I'm doing this a little bit different today. I'm on my laptop instead of my desktop, so let's see if this works. Okay, so in talking about acids and bases, there's two theories that we're going to discuss. And the first one is called the Arrhenius theory. And the Arrhenius theory says that when an acid dissociates in water, it contributes hydrogen ions to the solution. And we saw this when we were covering the unit on naming, how all acids begin with an H. So we can see here hydrochloric acid. When it dissociates into a hydrogen ion and a chloride ion. So it's contributing this H plus to the solution. And that's what makes an Arrhenius acid an Arrhenius acid. Now, the bases, when the base dissociates, it contributes an OH or a hydroxide ion to the solution. So an example of this would be sodium hydroxide, NaOH. When it dissociates or decomposes, you get a sodium ion and the hydroxide ion right here. Hydroxide ion contributed to the solution. So that's the Arrhenius theory, hydrogen ions for acids and hydroxide ions for bases. And this is probably familiar to us because we went through that unit on naming. Well, there are 6 acids that are considered strong acids. There's only 6. And what the word strong means here is that when it dissociates in water, that 100% of these acid molecules dissociate. So 100% of these, every single one of them break down into a hydrogen and a chloride. And you need to memorize these 6 acids that are strong, and every other acid out there is going to be not strong, which means it's going to be less than 100%. Some are as low as 0.01% or even lower, and some are as high as 98, 99%. But they're still considered to be weak acids because they don't dissociate 100%. Okay, and so these 6 acids you need to memorize are HCl, HBr, and HI. So it's in the halogen group. It's not fluorine, though. Fluorine is not considered a strong acid, but the next 3 are chlorine, bromine, and iodine. Those are strong acids. And then the polyatomic ions are HClO4, HNO3, and H2SO4. Okay, so these are the 6 strong acids that dissociate 100%. Anything else, all other acids are less than 100%, and as a matter of fact, they're going to have a Ka value. So remember, we were talking about KSP in our last section, where you have a solubility product because it's a low solubility compound. Well, since these don't dissociate 100%, they don't dissociate enough, then they have a Ka. So this A here is the dissociation constant for a acid. All right. And then as well, there are 7 strong bases that you need to memorize. And these are kind of easier to memorize because there's a trick that you use on the periodic table. And these 7 bases dissociate 100%. So it's all of group 1 except for the top element, hydrogen, and the bottom element, francium. So it's group 1 except for 1 at the top and 1 at the bottom. So that's going to include lithium, sodium, potassium, rubidium, and cesium. Okay, those are all strong bases. So it's going to be lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. Okay, now it's all of group 2 except for the top 2 and the bottom 2. So it's not going to include beryllium or magnesium, but it does include calcium and strontium. And then, of course, barium and radium, Ra. What is Ra? I'm not sure what Ra is, but barium and the one right under it, Ra, are not. So it's just calcium and strontium, calcium hydroxide and strontium hydroxide. And all of these other ones, it is radium. All of these other ones dissociate less than 100%. And just like the Ka, they're going to have a Kb value. Okay. And so just to recap, that's the Arrhenius theory. Okay. And before we go on to the other theory, let's talk about two vocabulary words, polyprotic and monoprotic. Okay. So this prefix here, poly, means many, and protic means protons. So a polyprotic acid is going to have more than one hydrogen that can dissociate from whatever the hydrogen is bonded to. Okay, and since hydrogen atoms have lost their one electron that they have, the only thing that's left for that hydrogen is a proton, because remember, hydrogen is one proton, one electron. And if you lose that electron, all you have left is the proton. So sometimes hydrogen ions are called protons. So that's where you get this name polyprotic. It's many protons or hydrogen ions. Okay. Monoprotic are going to be, mono means one, hydrogen. So these are the acids that only include one hydrogen. Okay, so some monoprotic examples would be HCl. See, we only have that one hydrogen. HBr, HNO3, etc. Only one hydrogen that can dissociate. And then polyprotic acids are H2SO4, H2CO3, H2S, etc. Or it could even be H3PO4. Okay, so if it's phosphoric acid, then it would be H3PO4. Sometimes these polyprotics, the ones that have two, H2 right here, sometimes those are called diprotic acids. And then if it's got three or more, that would be polyprotic. But technically anything more than one is going to be polyprotic. So if you see that term diprotic acid, just know it's H2 something something attached to it. Okay. The Bronsted Lowry theory of acids and bases is a little bit more difficult than the Arrhenius theory, but you just have to remember what a Bronsted Lowry acid and base is. And this is just another type of acid and base that we discuss. Sometimes Arrhenius acids are also considered Bronsted Lowry acids or bases. But the definition is just a little bit different. Instead of starting with an H or contributing hydrogen to the solution or ending an OH and contributing hydroxide, a Bronsted Lowry acid is defined as a proton donor. So it's any compound that can give up a proton or hydrogen ion to another element. So just think about it as being one less hydrogen because it had to donate to something else. Okay, and a Bronsted Lowry base are defined as proton acceptors. So those are compounds or elements that accept that proton, and that hydrogen becomes part of its new formula. Okay, and we can understand this more about looking at an example. So here we have hydrochloric acid plus water. Okay, so this HCl and this H2O, this dissociates, this HCl, and then water, this H2O, picks up one of those hydrogens. So we see here as our products, we have H3O. So this is the Bronsted Lowry base because it accepted the hydrogen, okay? And this is the Bronsted Lowry, the HCl is the Bronsted Lowry acid because it donated the hydrogen. Now, over here on the product side, if you have a Bronsted Lowry acid, it comes with a pair, like a partner. Like this is our Bronsted Lowry acid. Okay, so what is the pair that goes with this? Well, it would be chloride because the chloride, the HCl gave up its hydrogen to become chloride. So where this is the Bronsted Lowry acid, its counterpart right here is called a conjugate. This is not working very well. Conjugate base. Okay, it's not writing very well, and I apologize for that. I'm not on my regular computer. So, Bronsted Lowry acid, because it donates a proton, and this is its conjugate base because it is the counterpart. Now, the reason it's called a base is because now it can accept a proton. Let me clean this up a little bit. So that says base, and that's conjugate. C-O-N-J is how I abbreviate it, conjugate. C-O-N-J-U-G-A-T-E is how you spell it. Did I write it out? Right there, conjugate. Okay. All right. So the counterpart to a Bronsted Lowry acid is a conjugate base. And the reason it's called a base is because now it can accept a hydrogen. Okay. And accepting hydrogens, look, accepting hydrogens, acceptors are called bases. So it's the Bronsted Lowry acid and its conjugate base. Okay. It just means that it has one less hydrogen. All right, and so on this one, we have H2O, right? That accepts the hydrogen. So this is a Bronsted Lowry Bl base, okay? And its counterpart right here is its conjugate, CONJ, conjugate acid, okay? Because if we were going the other way with this, then this H3O could give up a hydrogen back to the OH here. Okay? So acid, conjugate base, base, conjugate acid. All right? And so below it says the HCl donates its hydrogen to the water and it becomes what's called hydronium. So H3O is hydronium. Okay? And HCl is the acid and the H2O is the base. Okay. All right. So if we were to look at this the other way here, now written this way, H3O is going to donate a proton or donate a hydrogen to the Cl. So this is the donor right here. So this is going to be the acid, Bronsted Lowry acid. Okay. And then H2O would be its conjugate base. Okay, now this is going to accept the hydrogen, so the Cl is the acceptor, so now it's the Bronsted Lowry base, and then its counterpart here is the conjugate acid. Okay, now both of these only differ by one hydrogen. Okay, all of these differ by one hydrogen. All right, and worth noting, strong acids like HCl produce weak conjugate bases, all right? And then strong bases produce weak conjugate acids. And vice versa, weak acids produce strong conjugate bases, and weak bases produce strong conjugate acids. So that might be a test question, something you want to remember on that. Okay, so that is the Bronsted Lowry theory of acids and bases. And there's one more theory. It's called the Lewis theory, but we don't study the Lewis theory in high school at all. Not even AP chemistry studies the Lewis theory. That's more upper levels of college. All right, so that is it for this section. It was really, really quick. It was like 15 minutes. So make sure that you slap that like button right across the face. Make sure you give me a thumbs up and a subscribe. So click that notification bell, and that way you know when new videos go up on YouTube before they do on Google Classroom.